Dear students, in this lecture we will learn how to derive the equation of beams on elastic foundation, the deflection equation, and also how to solve the general form of deflection of beam on elastic foundation. A general solution of elastic line. According to Hittini, the analysis of bending beams on elastic foundation is developed on the assumption that the reaction force of foundation is proportional at every point to the deflection of beam at that point. This assumption was introduced first by Winkler in 1867 and formed the basis of the Zimmermann's classical work on the analysis of railroad track, published in 1888. هذه البيمز on elastic foundation هي أحدى الطرق التي نتعامل معها مع الأساسات، وهو موضوع مشترك مع structure. يفترض وينكلر بأن السويل عبارة عن مجموعة من السبرينجز، كل سبرينج إلى stiffness إلى كي خاص به، واللي احنا نسميه الكوفيشنت اوف سبجريد رياكشن. وراح نلاحظ بأنه المعادلة التفاضلية اللي تحكم البيم أو من الأستيك فاونديشن مشابهة للمعادلة الاعتيادية اللي تحكم البيم مع إدخال تأثير السويل كسبرينجز. هناك there are many applications for this kind of analysis, such as construction of a floor system for ships, building and the bridges, foundations, also thin-walled structures such as pressure vessels, boilers, containers, large span modular reinforced concrete halls, and domes. The differential equation of elastic line can be derived as follows. Consider a straight beam. With length L, straight beam. This straight beam supported by soil along its entire length by a soil, and the soil is represented and considered as elastic medium, subjected to vertical force such as concentrated force, distributed force, in the principal plane of a symmetrical cross section. After deformation, the elastic line or elastic beam will be like this. Here, the elastic beam subjected to applied forces, and this is the soil pressure. The soil pressure can be replaced by K multiplied by Y. Y is the deflection and K is the coefficient of subgrade reaction. Let us take the following elements. This element from the elastic beam. Here Q, and in this side Q plus, and this side of element Q is the shear, Q plus dQ, because we consider element with thickness dx. Q dx is the applied force resisted by the soil pressure, P dx, which is equal to Ky dx. Now summation of y, apply equilibrium, summation of y, Q plus and down Q plus dQ with sign negative, plus Ky dx positive minus Q dx with sign negative equal to 0. Now divide entire equation, or before the dividing the equation by dx, q minus q will be removed, minus dq plus ky dx minus q dx. Because of this minus, the equation will be dq plus, not plus, this is equal to ky dx minus q dx, because there is a negative here, negative sign. Now divide the equation by dx, dq over dx equal to ky minus q. Where q is the shear force, k is the modulus of subgrade reaction, y is the deformation in vertical direction, p is the soil pressure, soil reaction, q is the applied pressure. Making use of the relation shear equal to dm over dx, the differential of moment with respect to x, dm over dx. Now replace dm over dx, q equal to dm over dx in this equation. Replace it in this equation. We get dq over dx equal to, instead of q now, q dm over dx, d square m over dx square equal to ky minus q. Now use the following equation for curvature of beam. ei d square y over dx square equal to minus m. Now replace m here with minus m, with minus ei, with minus ei, the fourth order differential equation of y to x equal to minus second order differential equation of m to dx. Replace this now in this equation. We will get ei, the fourth order differential equation of fourth order y to x equal to minus ky plus q. This equation now, this equation is the differential equation for deflection curve of a beam supported on an elastic foundation. Without ky, the equation represents the differential equation for deflection curve of a beam without supporting by elastic foundation. Along the unloaded parts, if this part, for example, is not unloaded, is unloaded, therefore q will be equal to 0, and the equation e will be ei, fourth order differential equation of y to x equal to minus ky. This equation can be solved by the following procedure. Take y equal to exponential to power mx. Now replace e to the mx in this equation instead of y equal to e to the mx. The fourth order differential equation will be m to the power 4 multiplied by e to the mx. Now replace this in this equation. You will get ei m to the power 4 e to the mx equal to minus k e to the mx. Now e to the mx will remove with the e to the mx, and m to the power 4 equal to minus k over ei. Divide the equation by ei. You will get this equation, m to the power 4 equal to minus k over ei. The roots of this equation will be m1 equal to minus m3. Since the power is even, m1 equal to minus m3 and m2 equal to minus m4, because it's even, because it is negative. Minus k over ei has negative sign, so the square root will be 1 plus I imaginary. If we replace k over 4ei by lambda, now m1 minus m3 equal to lambda multiplied by 1 plus I, and for the second m2 lambda minus 1 plus I. The general solution will be a1 equal to multiplied by e to the m1x plus the constant a2 e to the m2 x plus a3. Since the general solution is assumed, the general solution e to the mx. Now we get the general solution will be a1 e to the m1x, a2 e to the m2, a3 e to the m3, and a4 equal to e m4x. Now we can use the following form: e to the lambda plus I lambda. E to the m1, replace m1 by lambda 1 plus I, or lambda, it is the same, lambda plus I lambda. Replace m1 by lambda plus I lambda, you will get y equal to a1 e to the lambda plus I lambda x plus a2 m2 equal to minus lambda plus I lambda, a2 e to the minus lambda plus I lambda x plus a3 e to the m3 in minus lambda minus I lambda x, a4 minus plus lambda minus I lambda x. We can write e to the lambda plus I lambda in another form, like this form: e to the lambda x multiplied by e to the I lambda x. It is the same, and this form also similar to above form: e to the minus lambda x multiplied by e to the I lambda x plus a3 e to the minus lambda x e to the minus I lambda x, and plus a4 e to the lambda x e to the minus I lambda x. Now using the following forms and following equation: e to the I lambda x equal to cosine lambda x plus I imaginary sine lambda x, and e to the minus I lambda x equal to cosine lambda x minus I sine x. Use these equations in above main equation: y equal to a1 e to the lambda x, a1 e to the lambda x. Now instead of e to the I lambda x, replace this equation: cosine lambda x plus I sine lambda x. Continue. Plus a2 e to the minus lambda x multiplied by e to the I lambda x. E to the I lambda x, replace it by this term: cosine lambda x plus I sine lambda x. Continue with a3 e to the minus lambda x. Since e to the minus I lambda x, replace it by cosine lambda x minus I sine lambda x, and this is also by cosine lambda x minus I sine lambda x. Now y equal to e to the lambda x, here also e to the lambda x, a1 plus a4 multiplied by cosine x. Now take these two terms, e to the lambda x, a1 plus a4 cosine lambda x, plus I sine lambda x minus sine lambda x, here multiplied by a1, here multiplied by a4, I a1 plus I a4 sine lambda x, and then a2 e to the minus lambda x, a3 plus a2, or a2 plus a3 cosine lambda x, cosine lambda x, this cosine lambda x, plus I a2 minus I a3 multiplied by sine lambda x. From this equation we can write it in another form using a new constant c1, c2, c3, c4, where c1 equal to a1 plus a4, c2 equal to I a1 minus I a4, and a3 plus a2, and I a2 minus I a3 by the constant c3 and c4. We get the following equation: e to the lambda x c1 cosine lambda x plus c2 sine lambda x plus e to the minus lambda x multiplied by c3 cosine lambda x plus c4 sine lambda x. This equation is the general solution of the deflection of beam on elastic foundation. In this equation, lambda equal to the root 4th degree k over 4 ei. This term lambda includes the flexural rigidity ei, flexural rigidity of the beam. For example, if it is made from concrete or made from steel, the modulus of elasticity and moment of inertia of the concrete and steel, and so on. EI is the flexural rigidity of the beam, and K is the elasticity of the supported medium of the soil. K is the subgrade reaction of the soil, or elasticity of the soil. So in this factor lambda, we have included the flexural rigidity of the beam and the elasticity of the soil. 1 over lambda is called the characteristic length. Characteristic length, it is in the inverse length. Multiplied lambda by x, lambda x, will be, since lambda inverse unit of length and x is the length, this will be absolute number. Lambda x is an absolute number. Y equal to e to the lambda x c1 cosine lambda x plus c2 sine lambda x plus e to the minus lambda x c3 cosine lambda x plus c4 sine lambda x. It is the general form of deflection of beam on elastic foundation. The first derivative of this equation gives us the following relation, or the following equation: 1 over lambda dy over dx equal to e to the lambda x c1 cosine lambda x. Derive this equation with respect to x, dy over dx. The derivation of this equation gives us the following equation, which is the equation of dy over dx, a slope, which is dy over dx is the slope of beam. Derive the first equation, derive the slope we will get the following equation: 1 over 2 lambda square d square y over dx square. D square y over dx square is the moment. From this equation we can get the moment of the beam. And derive it for the third time, you will get this equation: 1 minus 2 lambda cubic d over dx for the third order differential equation. You will get the shear Q. So from this equation, from the general solution of deflection of beam on elastic foundation, derive it for the first time, gives us dy over dx is the slope of the beam. For the second time, the derivation of the second time gives us the moment. Derivation of the third time gives us the shear of the beam at any location in the beam.